I'm Caleb Walcott. I'm a PhD candidate at the University at Buffalo in the Geology department. So glaciers and ice sheets grow and shrink in response to climate change. And glaciers are also really good at eroding and moving materials. So this means as the glacier grows, it'll bring with it anything from tiny pieces of sand to boulders the size of cars and even houses. In the field, we go at these rocks with a hammer, a chisel, and a rock saw. And what we're really trying to get is about a kilogram or a softball size of rock to bring home back with us to the lab so we can figure out how many of these cosmogenic nuclides are in them.
As glaciers grow and shrink, they move around lots of material, including large boulders. These boulders are dropped as the glacier melts, and they begin accumulating beryllium-10 when they are exposed to the atmosphere. Therefore, I can walk along the line where a glacier retreated in the past and measure the amount of beryllium-10 in the boulders and figure out when the glacier retreated to that point and how fast it was retreating.
So once we've got this beryllium or this aluminum or carbon extracted and isolated, we pack these into little metal targets and we send this off to an AMS or an accelerator mass spectrometer facility where they count on these really big instruments how many individual atoms of beryllium or aluminum or carbon there are. And so they send this number back to us, right? And this is where the fun part begins. This is where we say, okay, we have X number of beryllium atoms. What can this tell us about how long this rock was here on the landscape, and what does that tell us about ice sheet history?
In fact, we can use math to help us figure this out. We can determine how long a rock has been exposed to the atmosphere using relatively simple equations based off the rate at which cosmogenic nuclides are produced in rocks and the half-life of that isotope. This tells us when the rock was dropped by the glacier as it was retreating.